Okay, good morning. So I have a little bit pain in my leg, so it's better for me to sit down and teach you. Hopefully this will also work.
Yes.
I'm also recording it, so everything should work fine, hopefully. Okay, so if you remember, we talked about permutations and we started solving some problems. Before going to the new lesson, let us start with some examples for warming up. Okay, so this is the example that you see here. How many permutations of the word table? Is it visible for you?
Yes.
Hopefully. How many permutations of the word table does a vowel appear immediately after T? Okay, so I think it would be a good idea if you pause recording a little bit and give you time to answer the question. This is a very simple question, but I want to give you time to refresh your memory a little bit, and then after that I will come and solve the problem. So I will give you 3 or 4 examples, and then we go to the next lesson, then it will start solving some new examples as well. Okay, please start thinking about it. Okay, do you have any answers? No answers yet? I mean, this combinatorics needs a little bit of new way of thinking, so you need to get used to how to think about it. It's the nature of the problem. So I will give you a little bit extra time because the problems are actually very easy. By the way, I think Grammarly made a grammatical error. Yes, it doesn't make sense. I put in how many permutations, but Grammarly, I don't know, for some reason, dropped that in. Yes, and the sentence doesn't look right, does it?
No.
No, but in how many permutations of the word table does a vowel appear immediately after T is probably correct one. So you put in back, yes? That is not my fault, that's Grammarly's fault. Yeah. By the way, in the book, when you read it, the explanations are very simple. The example they pick up is very simple, but I don't know how many of you have started looking at the exercises in the book. Sometimes it becomes harder. But the things that I am presenting here, you might think that this is above the book, but no, when you go and solve the problems, you will face them. So if you don't have the clue how to think about them, then it is not possible to solve those problems. When you have your answer, please let me know about it. Yes, Gustav?
Is it 12?
Can you, I don't think 12, I don't know, I have to calculate, but can you give me in terms of factorials and things like that?
2 factorial times 3 factorial.
So you're saying 2 factorial times 3 factorial, yes, so that's your answer. Let us check. Any other answers? Okay, how do you think about the problem? So we say that, okay, I have a word table. Yes, it includes 1, 2, 3, 4, 5 letters. All of them are distinct. And then what I want, when I want to write a permutation of this word table, I need 5 positions, yes? Okay? And then you have some constraints, you have some obligations to respect. You want to write T in a way that immediately after T a vowel appears, yes? So, for example, you can immediately realize I cannot put T here, because if I put T here, there is no other space for putting that vowel. So you need to usually start, by the way, if you really want to do that, this is an easy task for every person, yes? You can definitely write this. Okay, how do you write it, by the way? How do you think to write it? You decide a position, for example, for T, yes? And after T, you decide about a vowel coming after T. and then because there are no more constraints there, you put the other letters there. That is why this is not acceptable for me if you don't have the correct answer. Because when you can write it, in principle you should be able to count it, unless the problem is so complicated that needs a little bit of creative thinking about how to do that. Isn't it natural? If you want to write a permutation of these letters, okay, so you need to fix the position for t in a way that you can still have a position on the right to put the vowel in, and after you put the vowel in, then everything is fixed. You just put the letters there. Okay, now can you help me? I want to be a little bit summarized in my writing. So yeah, let me write stage 1 if you want to. So let me write stage 1. Okay, assigning a position for t. Okay. For example, a stage 2 is assigning a letter, a vowel, coming immediately after t. Yes? I mean, this is the way that you need to think. And then can you say something about stage 3? Because if I just do a stage 1, after that stage 2, I hope that you agree the task is not accomplished yet. Because what happens with the rest of the letters? So what is a stage 3?
Arranging the remaining.
Yes, arranging the remaining letters. Remaining letters, or if you want to be more precise, remaining letters in remaining positions. Yes? Okay, now tell me in how many ways I can do this stage. Number 1.
One.
No, assigning a position for t.
Oh, never mind.
So where can I put t? I can put t here, 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 but not there. Do you agree? So there are only 4 positions that I can put t in. So I would say that, okay, this stage number 1 can be done in 4 different ways. Okay, now you have to assume the first stage is done in any one of these ways that you mentioned. Okay, for example, for definiteness of discussion, you can assume that you put your t here. Okay, that's not, but of course you have to be careful about independence. Okay, and then you go to stage 2, assigning a vowel coming immediately after t. So how many vowels are there? 2, either A or E. So how many choices I have for the second stage? How many options?
2.
2. Now, when you write 2, you have to be a little bit careful, okay? Is this 2 that I write here independent of how I have done the first stage? It means that, do you think if I put t here, this will change this number? No, if I put t here, still I have 2 options, either A or E. If I put t here, still I have 2 options here. So it does not affect actually this number. Okay, now after this is done, it means that you chose and put something after t. For example, let us say that I put, I don't know, I put E here. Okay, now what is gone? T is gone, E is gone. How many letters are left? 3. These are independent, these are distinct objects, A, B, and L. And how many positions are left?
3.
3. And then you want to put 3 distinct objects in 3 distinct positions. So how many? 3 factorial, yes? So what you can do is you can write that this number is n3 is 3 factorial. Okay? So finally, the answer to the question mark is what? By the way, you also need to check, is this 3 factorial that you answered is independent of how the first stage and the second stage are done? Yes. But always you have to check it out, okay, even if you don't write it. If this is correct, and then what is the answer? It is 4 times 2 times 3 factorial. So the answer is 8 times 3 factorial. And of course, if you want the final answer, 3 factorial is 6, so just write 48. But I just don't care. If you just stop here, that's even better. So you just, unless I explicitly mention that, you have to give me the answer. So if you don't mind, let me clean this, yes? That was not correct. Is that clear? Okay, now that I refresh your memory a little bit, so I want to wait for you to solve that problem. Might be next time I have to make it bigger. Is it visible from the last part? Yes, is that clear? You can see it at the end. Okay, so it's not that small. So how many, this is also I think it is in the book. So how many ways can 10 people stand in a queue if 2 of them do not want to be next to each other for some reason, okay? So let us try to solve that problem. Okay, any answers? Oh, let me change them. Okay, any answers? Yes?
8 times 2 factorial times 8 factorial.
Okay, so let me write it down. May you repeat it, please?
8 times 2 factorial times 8 factorial.
Times 8 factorial, yes. So let us check. Any other answers? Yes, Rocco?
I got it 10 times 2 times 8 times 8 factorial.
10 times 2 times?
8 times 8 factorial.
Times 8 factorial. Okay, so this is also question mark. Are they the same or not?
They're not the same.
They are not the same, okay. Yes?
I got 8 times 2 times 8 factorial.
8 times 2 times 8 factorial?
Yes, which is the same
As the first one.
Yes.
Yes, so yeah, so they're more or less the same thing, okay. Any others? Okay, can you describe how did you come to the answer?
I choose a place for 2 people where they have 1 person between, and then I arrange the remaining people.
Okay, how many of you agree with this strategy? No, because if so you force them exactly 1 person to be in between. Yes? But that is not what problem demands. Yes? What you need to be careful about is that there should be at least a person between them. Yes? So that's important, by the way. You need to interpret the question exactly what it means. Yes? But still, I don't know if you have done it correctly or not, but we can also check that if this is correct or not. But this is not what is demanded in the problem, yes? Because one scenario is to put 1 person in between them, but it might also be the case that I have 2 persons between the people who don't want to be. Okay, so you haven't considered that scenario. And then Robert, I don't know, did you think the same way? Because your answer is the same.
Yes, I misunderstood.
Yeah, so, but I hope that you agree that this way of expressing this, it doesn't force you to put exactly 1 person between them, yes? Yes?
Well, what I started with was first I thought that the first person could be in any place,
Mm-hmm.
and then the second person could be in 8 or 9 places, depending on whether the first person is in the middle of the line or at the edge or not.
Okay, so you need to consider a lot of cases, you mean? Because in that case, you need to because the product rule is not enough, because you say that either that or that, it means that after doing some product rule, you also need to use some rule, yes? Yes. Might be this is working, because this is easy in this case. I have 2 people disliking each other. But you can also extend the problem of what happens if I have 3 people don't want to be each other, okay? In that method, the number of ways that you want to consider becomes so huge that you have to consider a lot of cases. So is there any better way to do that? That will work, okay? At least for this case. But do you have any better way to do that? I can give you a hint, yes? So we had 3 rules, not 2 rules. Yes? Usually 1 rule is very obscure, but do you remember the rules? We have, the first one was the product rule, and then the sum rule, and there was another one. The complement rule. Okay, so can you tell me how complement rule will help me to solve this problem easier? Yes.
You could calculate all the situations where they are next to each other.
Yes.
And then subtract.
And
Um,
so I need to calculate the all possible arrangements without any constraints at all. And then I consider all the arrangements in which these two people are next to each other, and then subtract it from the total number of possibilities. And what is left, it means that I am counting those cases in which these two people are not next to each other. And it doesn't matter. I'm just counting them, they are not next to each other. So it means that it considers all possibilities, yes?
Isn't that just the 10 factorial minus 9?
No, we will come back to that one. But I hope that first of all you agree my strategy in counting, yes? So the total number of ways that I can arrange these people next to each other is very simple. So what is that?
10 factorial.
10 factorial. So it's a very easy problem. So 10 factorial. This is the total number of ways. But in how many ways I can arrange this Q line so that these two people are next to each other? So these examples that I provide here, even though combinatorics is a discrete mathematics topic and people think that there are no very decisive way to teach it, but these examples that I present here, you can consider them as model examples, okay? So in this case, I want to count the number of possibility of arrangement of these 10 people in a queue in which two people are next to each other. Do you remember? Can you compare this with one of the model examples I presented before? Do you have some idea? We discussed about, we had some bookshelf and then we had some topics, we want to put them next to each other. Okay, so in principle you should be able to answer that one. So how can I do that? The problem is that I have 10 person here, so person number 1, person number 2, and up to person number 8, person number 9, and person number 10. Let us assume for definiteness of discussion that these two people have actually problems, okay? So in how many ways I can arrange them intentionally so that P9 and P10 are adjacent, immediately adjacent? So how many ways I can do that?
9?
No, 9 factorial is not correct. That was just 9. No, that is much more than that, isn't it?
Can you say the question again?
In how many ways I can arrange these objects? Now, for mathematics, people are just objects. In how many ways I can arrange these objects? The answer was 10 factorial, which, by the way, is a very big number. Because I remember 8 factorial is 40,000 something. And you multiply it by 9, and you multiply it by 10. So it would be around 3 million or something, okay? So that's a huge number. So 10 factorial is the number of ways that we can arrange these 10 objects. These are distinct objects, so they need 10 distinct places. So this is 10 factorial. But in how many of them P9 and P10 are immediately adjacent? How we can count it? You should have a strategy. Yes?
Couldn't you count P9 and P10 as one object?
Okay, so that's the idea. Do you remember exactly the idea with the books that we have? Yes, for example, what can I do? I can assume that I can put them in a bundle like this, yes, and put a capital letter P on top of that. Then how many objects you see? You have an orange capital P, which is distinct from the other P. So in general, in total, I have 9 distinct objects, and I want to arrange them. But this box will move around, okay, with these two people inside it. So I would say that there are how many of them? 9 factorial is the number of ways that I can arrange P1 up to P8 and a capital P together, okay? But these two persons can also interchange among themselves, yes, in 2 ways, or we say 2 factorial way. So I have to multiply it by another 2 factorial. Is that right? Is that understandable? Okay, and then, so what is the answer to the question mark finally? So the answer is 10 factorial minus 2 factorial times 9 factorial. And what I really expect you to write for me is just this answer. Or of course, if you have a different strategy, I will check it out as well. Might be that strategy is also correct. But first, I want you to understand that this is working, or is that right? Yes? Okay, so this is the total number of ways we can arrange these people. And this is the number of ways that we can arrange these people in a way that P9 and P10 are adjacent, immediately adjacent. But I want them not to be adjacent, so I take it off from the total number of ways I can arrange them. So what is left is the answer to this question. Is that clear? Okay, so hopefully it is clear. So somehow also think about a complement rule. Okay. There is another strategy we can count that, but we need to go a little bit further in the lesson. So for the time being, remember these tricks. These examples that I'm providing in my teaching are actually model examples. If you have them in mind, you can compare different problems with these problems and then try to solve it. Okay? Yes. So forget about, I don't know, I was testing something. So there are 6 different shoe pairs. How many ways can one distribute these shoes among 5 people so that each person receives a right-footed and left-footed shoe? A right-footed shoe and a left-footed shoe. So Grammarly actually destroyed my sentence. Okay. Anyway, so there are 6 different shoe pairs. They are completely different shoes. In how many ways can one distribute these shoes among 5 people so that each person receives a right-footed and a left-footed shoe, and the remaining 2 shoes make up a shoe pair? Yes? Is that clear? Yeah. I mean, the questions are not hard to understand, but solving them might be a little bit hard. So you have to have a strategy. Yeah, if you don't mind, let me wait. So, do you want to ask some questions?
So when it says and the remaining 2 shoes make up a shoe pair, they don't have to be the same type of shoe. It could be like if there's one black shoe.
No. It's a shoe pair. I mean, the shoe that you buy from store.
No, but what I mean is like if there's a right black shoe and a left pink shoe, it's okay if they make up the last pair. Is that what it's
No, that is not a normal pair of shoes. Normal pair of shoes are identical, but one of them is right, one of them is left.
Okay, so they have to be the same shoe.
Yeah, exactly. The shoe that if it fits to your foot, you can just put it on.
No, but I don't mean like the shoe size. I mean the type of.
No.
Because there are 6 different shoe pairs, right?
First of all, by the way, I think this English is correct. So it is important to interpret the question in a right way yourself. Because this is just one of the problems in combinatorics. People think they can read different things from the same sentence. Yes? So try to be so the remaining 2 shoes make up a shoe pair. When you say a shoe pair, it means that it's a shoe pair, yes?
Yeah,
So what does it mean?
Of the same type of shoe.
No, but we shouldn't express this one. If I ask you, can you bring a shoe pair for my birthday? You just bring a shoe pair for my birthday.
Yeah, but theoretically.
No, theoretically, no. This is we are talking about what is happening in real life, and we want to count them. Yes, that is one thing I want. So don't be like a computer coder here. So that everything should be clear. I am relying on our human conversation, yes, and what we know from the other world. But in principle, you are right. Because in principle, you can say that one person there are people, by the way, putting on shoes with different colors, yes? Don't consider those cases, yes. So, if I want to fix it, so if the grammar is, there are 6 different shoe pairs. Yes, different shoe pairs. This is one shoe pair, that's another one. They are distinct. In how many ways can one distribute these shoes among 5 people so that each person receives a right-footed and a left-footed shoe, and the remaining 2 shoes make up a shoe pair? I want to think about it, yes? Let me just repeat it because I think it's important. Is it possible for you, if I give you this situation, I give you shoes and I show you the people, do you really can do the task?
Yes.
If you can do the task, if you think how your brain is doing the task, then probably, hopefully, you can also count it. But think what you do in principle. Yes? And whenever you are ready, give me your number. Okay, so too quick. Yes, I just write it down here for you.
6 times 5 factorial squared.
6 times 5 factorial squared.
Yes.
Okay, so let me just put a question mark around that. So let me write if you agree with me. You said 6 times only one. This one you mean?
Exactly, not factorial squared.
Okay, so this is 1. Anyone else? But again, I'm telling you, these are not higher than the level of the questions in the book. The way the books teach is different from the exercises that they put at the end. Yes, Robert?
Isn't it 6 factorial squared?
Okay, so this is another suggestion. So you see, this is the nature. But one of the answers, if any, should be correct. Yes, Cam?
6 factorial?
Just 6 factorial. Any other answers? By the way, it's a very exciting subject, isn't it?
It's nice.
Yeah.
5 factorial squared är 6. Jag har den första.
Okay, so I don't know. Gustav, you told me, can you explain your strategy?
Sure.
Mm-hmm.
So, in stage 1, I picked 1 pair of shoes to give to the last person. And there are 6 pairs of shoes to pick from. So, we have 6 possibilities. Then I distributed the right shoe to the remaining 5 people.
Mm-hmm.
Since there's 5 right shoes and 5 people, that's 5 factorial.
Mm-hmm.
And then I distribute the left shoe to the 5 people.
Mm-hmm.
5 shoes, 5 people, 5 factorial. So that's 5 factorial times 5 factorial times 6.
Yeah. Is it right or not? Yes?
I think I have the same answer as Camille, which is 6 factorial.
Yes?
Because I think like if it's 5 people and then 1 place, then it's like regarded as 6 places.
Yes?
And then there are 6 pairs, so it's just 6 factorial.
But of course, in that case, you are distributing 6 pairs. Yes? When you say 6 factorial, it is one possible way of doing the task. Yes? It means that you have the people in a row, and then you just have 6 pairs, okay? And then put them in front of these people. This is not wrong, but this is not the only possibility, because now you can play around with different pairs. Yes, for example, I can pick a left-footed shoe from one pair and match it with the right-footed shoe with another pair. We can do that for these people, unless the very last one, they have to be a pair. Yes?
Yeah, I don't know if it was mentioned, but 6 times 5 factorial is the same as 6 factorial, but just to be clear.
Yes. 6 times 5 factorial is just as so. So this means these 2 answers are actually identical.
Yes.
Yes. But there is still a difference here and there. So.
Yeah.
Okay, so the way that I want to do it, I think it's very close to Gustav's method, okay? But I will do it in my own way. So what I do, if I really want to do that, I know that there should be a shoe pair left at the end. So I just take it and throw it away, because this is going to be left. So among these 6 pairs that I have, I choose one of them. In how many ways I can do that? 6, because there are 6 pairs in front of me, I can choose. So I would say that there are 6 ways to choose that pair. Now I am relieved. I don't need to be worried about doing this right, because I have 1 pair reserved. Yes? And then I exactly do what you said. So I have peoples in front of me, and how many left-footed shoes I have?
5.
5. Okay? And how many right-footed shoes I have? 5. So the people are standing in a queue. I take the left-footed shoes and distribute them in front of them. In how many ways I can do that? 5 factorial. So the first part of the task is done. So there is 1 shoe remained. I am relieved from that one. Then I took the left-footed shoes and distribute them among the people. I can do it in 5 factorial ways. But this task is finished, and there are 5 left-footed shoes left for me, or the other way. Yes, and then I distribute them again. So that's your answer is completely correct. Yes, let me just write that. So the answer is times 5 factorial times 5 factorial. So either you can write it as what Gustav mentioned, 6 times 5 factorial to the power of 2. There is also another way to do that. So let me clean this, we don't need them anymore.
6 factorial times 5 factorial.
Yes, because now you can either combine them in that way, or you can say I combine these two, it becomes a 6 factorial, then I have a 5 factorial, yes?
Yeah.
So then it becomes 6 factorial times 5 factorial. So both of them are actually correct. Yes, Rob?
Yeah, I was just confused but so theoretically, if we among these 5 pairs, I know, but it's important that I understand.
Yes.
This. So one person can have a black shoe and a pink shoe, for example, because they're different pairs.
Yes.
Yes, one person can have.
Okay, so I just misunderstood it then, because I asked about the remaining pair. But the remaining pair, of course, will have to be the same.
Yeah, that was I was confused why you were asking.
Yeah,
Yes.
So what I was actually referring to in reality, but I didn't perhaps express it correctly, was the 5 pairs. They can be
exactly.
Okay.
Yeah, exactly.
Because my method only considered if you just distributed the same pair.
Yeah.
So then it's 6 and 5 factorial.
Okay, but now you understand what's going on.
I understand. I understand.
And do you agree with me that was also clear from the question?
Yeah, it was clear.
Yes. So that's what I'm saying. Try to fix this in your brain, because sometimes you not for my questions. You read it in the book, and then you see the answer is different. You think that your interpretation is correct, but the interpretation is not correct. So that's something that you also need to fix in this lesson. Okay. So usually from my experience is that when we can express the answer like this, it might be able to understand this directly. So here we solve the problem in 3 stages. But it shouldn't be a coincidence that they can combine. So this means that if a person is probably smart enough, they can do the task in 2 stages. Can you realize why 6 factorial times 5 factorial can also be correct from the beginning? Instead of solving the problem in 3 stages, I and Gustav solved the problem in 3 stages. And I couldn't foresee this before. But now I see that I can write it as the product of 2 factorials. Might be there is a smarter way of counting the same situation, not in 3 stages. By the way, the people who are interested in algorithms, this is important. Because now we are doing the same thing. Is it possible to do it? Yes, please, Rob.
First you give out the first 6 right shoes.
Yes?
And then you match the last, or one of the left shoes with its pair. And then you give out the remaining 5 shoes to the left.
So let me think. So you say that the people are standing, what do? We have 6 right...
All the right shoes, so it's 6 factorial.
Yes.
And then you give out 1 shoe so that it matches its pair. And then you have 5 factorial.
Yeah. So in that way, you really can count it in 2. There's 2 stages, not 3 stages.
Yeah.
Yes? So you see, it is very good, but the people who are working in coding and they want to have more efficient algorithms, these are important things to think about. Yes? So this can also be done in 2 stages from the way that you gave us this story. Yes? Okay. Okay, so let us go. The next problem probably is a little bit hard now. So you are more experienced, you can solve harder problems. So in how many permutations of the word mailbox are the letters A and M adjacent, but the letters B and X not? Or are not? I am just confused with grammarly. Which one is correct? Anyway, so that you understand what it means, yes? So I want to look at all permutations. First of all, if I ask you all the permutations, it's easy. 1, 2, 3, 4, 5, 6, 7. I have 7 distinct objects, so 7 factorial is the total number of permutations of these objects. But now I have 2 very important constraints. I want, first of all, A and M be adjacent. And secondly, which is probably more important to consider, is that B and X are not adjacent. So there are two constraints to satisfy for this one problem. So it's more interesting. So if you can solve this problem, it means that you're really on the safe side. You understand everything, okay? It doesn't mean that you can solve all the problems because they're extremely hard sometimes. But let me give you a little bit of time to think about it. And as usual, when you have your answer, please let me know. Yeah, the people who are good in programming, I want you to write a code that generates all the lists. Can you, Rocco?
Yeah, I could.
Yeah. Do you have computer in front of you?
Yeah, I could do it. I mean, it depends on if you want me to do it manually. I mean, there are modules that can literally give you all the permutations of a string. Like, if you just...
No, I don't exist. You can use the modules.
Okay.
But I don't think they have a particular modules for this particular situation, yes?
No, but what I'd do, so I'd use the module to
Yeah.
generate all the permutations,
Yeah.
and then I'd run and then I'd loop through them and filter out the ones.
Okay, you can work on it as well, because we want to check if it is going to work
It
or
would
not.
essentially be like the complement there. So you generate all the permutations.
Yeah, but you have to use the complement rule in a very wise way.
Yeah, exactly.
Yes. So,
I mean, that's,
yeah, you can do that. Yes, that's a good idea. We can check our answers.
yeah, I can do that right now.
Yeah.
So
I think so.
Okay, so just give me. I write it down. I still give time to people to think. Yes, please.
6 factorial minus 5 factorial.
6 factorial minus 5 factorial. Okay, so 6 factorial is 720, and then this is 120. So this is around 600. Not exactly. You are saying exactly 600 items. Yes. I don't know how Rocco is acting so correctly.
I'm writing.
Okay.
It's had to.
Do you have your answer?
Maybe 2 factorials times 6 factorial.
Just wait, please. 2 factorial times 6 factorial.
Minus 2 factorial times 5 factorial.
So that's 60.
Okay, so you're essentially having the same answer as Aaron, but you're just multiplying it by 2, yes? Because if I factor a 2 factorial out, that's the same answer as Aaron, but you are saying that it is 2 times larger than what Aaron proposed.
Yes, I made a mistake.
So you agree with this one now?
Yes.
Because what Tino is mentioning is the same number as you mentioned, but multiplied by an extra factor of 2. Because if I factor a 2 factorial out, it becomes your answer multiplied by 2.
Because I missed that you could arrange them in either AM or MA.
Yeah, okay. So now you agree with Tino's solution. Okay, still I want to give chance to others to think about it.
But I had it at the X. Yes, we. What is that?
Oh, you also got the same answer. So, first of all, tell me, is mailbox itself acceptable or not?
Yes.
Yes? Because M and A are adjacent, and B and X are not adjacent. So the mailbox, the word mailbox itself is an acceptable item, yeah? So you understand what the problem is, yes? Okay, Tino, can you describe your method?
Well, you group A and M together in a box, and then they can also interchange, so it's times. So it's 6 factorial, because you have 6 items, and yeah, times 2 because they can interchange.
Okay, so what you are doing, you are not using the complement rule on the total number of items. You are using the complement rule on the items which already have M and A adjacent. Yeah, that's the correct strategy. Yes, because if I want to describe it for you, so some of you might start. So let me just try to describe it as best as I can. So if I draw this one, I just want you to understand the complement rule shouldn't be used on the total number of items, yes? So the total number of arrangements, yes? The total number, permutations, yes, of mailbox. Okay? So this is the total permutations of mailbox. So I hope that you agree with me. One part of these items, I don't know what they are. So this is the part. Here, this is what some of them have M and A adjacent regardless of what is happening for B and X. Yes? So what I want to put in this yellow curve, I put the items from the total number of items for which M and A are adjacent, and I don't care about what is happening to B and X. Some of them are adjacent, some of them are not adjacent, yes? So here, M is adjacent to what? To A. Okay, so but this is now, I hope that you agree that I can also subdivide this one itself to two groups. I'm not considering the sizes, yes? Some of them all B, so let me write it like this. So here, for example, assume that this part B and X are adjacent. And then this part B and X are not adjacent. Is that clear? So which part I want to count? This is my question mark. Do you agree?
Yes.
This is, I want to answer how many items are there. This is what I want. Is the diagram clear? So you see that this big rectangle is not playing in that much role. Yes? Because what I want to know what is the total number inside here, and I want to know how many of them are here. Then I want to take that part away. I don't know if the answer is correct, but now, do you think your answers are correct? Okay, let me ask you. Can you tell me how many items are in this curve? It means that there is one constraint to M and A should be next to each other. So what I do, this is again a model example. You know what to do if I want to have two things next to each other. So what we do, I will do it like this. I would say that M and A, I put them in a box. Yes. And then I have what? Mailbox. Mailbox. Okay, so how many of them are here? So can you tell me? M and A, I consider it one object. Second, third, and 4, 5, 6 objects. So 6 factorial times 2 factorial. Why this 2 factorial is coming? Because 6 factorial tells me how can I arrange this one particular object with these 5 objects. It becomes 6 factorial. After it is done, I can also have the freedom to arrange M and A within itself, yes? So that is why I multiply it by 2 factorial. Okay, now what happens here? I want to count what happens that if B and X are also adjacent. So you see, this is already counting M and A to be adjacent. This part, B and X are adjacent on top of M and A being adjacent. Yes? So how can I solve that problem? I would say that, okay, now I put MA in one box, yes, something like this, and then I have I, L, B, and X in another box, yes, and there is O there. Do you agree? So now I count how many situations are in this form. So how many situations are in this form? How many objects you see? This is one object, 2, 3, 4, and 5 objects. Okay? So 5 objects I have, so it becomes 5 factorial. But what should I multiply now? That's your mistake, I think. Can you see that now?
Is it 2 factorial? 2 factorial?
2 factorial times another 2 factorial. Yes? Because you are counting what? So you see, you understood that you are supposed to count the total number of items like this. If I ask you this, what do you answer? You say 5 factorial because of 5 objects, but 2 factorial because of the arrangement of M and A, and 2 factorial because of B and X. So 1 2 factorial is not enough, so you have to multiply by 2 factorial, 2 factorial. Yes? Okay, and then what is the question mark? The question mark is what you said, 6 factorial times 2 factorial, the total number of items, not in the rectangle. You realize that it is irrelevant to our discussion, but minus, so let me write 2 factorial times 2 factorial times 5 factorial. I don't know if Rocco has finished.
I'm almost finished.
Okay, so
I just realized I did a big mistake, so I should like rewrite it.
yeah, I mean, okay. So can you calculate the final number now, so that we can compare with what is Rocco is going to compute? Okay. So what is the answer? 6 factorial. Can we simplify this a little bit? So let us just calculate it. It's very simple. So 6 factorial is 720. You multiply it by that, it becomes 1440. And then 5 factorial is 120. Multiplied by 2, 480. And if we subtract them, it becomes what?
960.
960. So this is our answer. Okay? First of all, tell me, is there any question? Do you understand what is going on? Yes, please.
Can you repeat why it's 2 times like 2 factorial?
No, because so here, what I am counting, I realize to answer this part. So you see, B and X are adjacent here. B and X are not adjacent here, and this curve contains M and A adjacent. So if you want to count this part, you have 2 constraints. M and A should be next to each other, so I put them in a bundle. And B and X should also be adjacent, so I put them in a bundle. And then I ask you count the number of arrangements of these objects. So how many objects I have? I have a bundle, like a curved bundle, and I have a box bundle. So these are distinct objects. 2 objects so far, 3, 4, 5 objects. So I multiply by 5 objects. But I have 2 degrees of freedom here, because I can write MA or AM, still they are adjacent. And for this one, I can write BX or XP, still they are adjacent. So 1, 2 factorial is coming from the freedom on M and A, and 1, 2 factorial is coming from the freedom on B and X. So you have to multiply by 2 and then subtract. Yes? Rocco, it's not working?
I think I got the answer to 1,440, but that's not your final answer, is it?
No, so 1,440 is just the first part.
Okay, so I did something wrong.
Yes, yes?
Yeah, I made a program with 960.
960? Okay, good. So at least we are in the right track. Yes? Any questions? Okay, so now let us see what is left. Okay, this is a new lesson, so if you don't mind, let us also start a little bit of new lesson today. So here, you see, this is in principle, you cannot solve it right now. Of course, this is so simple that you can write all the items and count them. What I'm asking you, so again, yes,
I solved it now, I just have to switch one thing.
it's 900.
160.
So it's confirmed. Yeah, so our calculation is correct. So I don't know. So I should, next time I have to, don't rely on, I don't know why. Grammarly is actually doing great, but not this time today probably. So how many permutations of the letters A, and B are there? Yes? Okay, so this is extremely simple problem. You don't even need a formula. You just write all of them and count them. So, but I hope that you agree the answer is not 3 factorial as before. Yes? Because it doesn't matter if I interchange 2 A's, they are identical. Yes? So, how many ways are there? So, let me first write them down, all of them. So, one of them is AAB, the other one is ABA, the other one is BAA. Can you imagine something else?
No.
So, these are the only permutations. So, I have this. Okay. So do you have a strategy to be able to count this? By the way, these are very model examples. You need to have them in mind. So what I'm asking you, what happened? Of course, this was so simple, you know the answer is 3. But let us, for example, imagine this scenario. I have 3 A's, I have 2 B's, I have 4 C's, and I have 1 D. and I ask you to arrange them in a row, how many ways you can arrange them? I hope that you agree that if you don't have a quite good strategy, then this is hopeless to start writing all of them down. Yes? So I want you to not only tell me the answer, give me a strategy that can be extended to the harder cases, like the orange one that I have written here now. The idea behind this is also a very important trick in combinatorics, that is double counting. Yes, let me just describe it for you. So, let me clean this. So what we think about this, even though A and A are identical, but momentarily I can put an index for them, say the first A, there is no first A and second A, they are identical. But for the time being, I imagine that A1 and A2 are distinct. A's are distinct. Okay, this is the strategy. You need to learn the strategy. Okay, and then what I say is that whenever you write an item here, start permuting A's among themselves. Do not touch B. Okay, so what will happen? If you want to do this, you do not touch this B. B is already there, but you interchange A1 and A2. What do you get? A2, A1, and B. Yes? These two items are distinct if A's are really distinct. But these two items should be counted only once if A's are not distinct. Do you understand me? Yes? So if I ask you how many items you see here, of course, this is one item and this is another item because you see the difference now with indices. But if you remove the indices, there is no difference between these two items. And that is my goal. My goal is not to count the ones with distinct A's. I want to count. Okay, but this is important. Let me go a little bit further, okay? Let me write another item. For example, A, this time B, and A. This time I give them index again. But the rule was this. Rearrange A's among themselves, okay? So in this case, A is occupying the first and the third positions. So if you want to rearrange them, but you have to stick to this rule that you should occupy only the first and the third for A's. Okay, what happens? How can I do that? I can write A2 here, B here, and A1 here, yes? If I want to stick to this rule, this one will not generate any new item for me. Okay? Okay, let us go to another one. So another one is what? I have B here, A1 here, A2 here, and the rule is the same. You are allowed to interchange A's, but you're allowed to interchange them only in the location that they have. So this becomes B, A2, A1. Yes? Is that right? Okay, so the point is that what I want to ask you, can you tell me what is the depth? So you see that I have a rectangular array of items. It has some number of rows. It has some number of columns. Yes? Okay, so can you tell me what is the depth of this table? Of course, you can see it is 2. But can you find a strategy in general? What should be the depth of this table? If I have 3 A's, not 2 A's. If I have 4 A's, what do you think will be the depth, yes?
I guess the amount of A's.
No. In this case, coincidentally, yes. Yes, Maria?
Number of repeated items.
No, he said the same thing. Yes?
Is it the number of like?
No, think a little bit about that. Did you realize what I did? I don't want you to spoil the problem, you know? So here, I told you what to do. You write an item, and the rule is to interchange A's among themselves and go down and down, down, okay?
Yes.
So how many ways you can go down? In this case, of course, 2, but let us assume that you have 3 A's. What do you think will be the depth of this column? If you have 4 A's, yes?
Is it the factorial of the number of...
Yes. Because what I told you that you are forget about these B's, you are going to arrange them. In how many ways you can arrange A1 and A2? 2 factorial. If you have 3 A's and they are distinct and you are supposed to arrange them within their positions, in how many ways you can do that? 3 factorial. Yes? Is that understandable?
Yes.
Okay, so the depth is of course 2, but if you want to write something in general, the depth is really 2 factorial. Yes? Okay, now what you want to do, you want to count the number of columns. The number of columns is something that we don't know. Of course, here we know it is 3, but in general we don't know. Yes? Why I say this is your question mark? Because what do you want to count? You see, you want to count only these, one of them from each column. Yes? Because if A's are not distinct, how many times we should count this? Only 1. And if A's are not distinct, how many times I should count these two? Only 1. And how many times I should count them? Only 1. So X, I hope that you agree, X is the number of the ways that I want to count. Yes? Is that right? Yes or no? Okay. So, but on the other hand, I know the total item here. Yes? What is the total number of items? 2 factorial times X. This is the total number of items. On the one hand, I counted the total number of items in this rectangle in one way, but I already know what is going to happen in a different way. Do you think what should be the answer at the end? Yes?
X divided by vector.
No. So I'm just telling you that.
Divided by the rows.
Let me tell you once more. So you know, first of all, you understood hopefully that the depth should be 2 factorial. Yes? Do you agree with me the question that I am looking for this problem is the total number of columns or not? Yes, because I want to consider the case in which A's are identical. Yes, so it means that from this column, how many items are acceptable for my situation now? 1. From this column, how many items is acceptable? 1. From this column, 1. So it is clear the number of columns is the one that I want to count.
Yeah.
Is that right? Okay. Now, so the number of total columns is still we don't know in general situation. The depth is 2 factorial. If I tell you that I have a rectangular whose depth is 2 factorial and its width is x, so how many items you see in the rectangle? What is the answer? Is 2 factorial, the depth multiplied by dx. This is on the one hand. This is one way of counting the items. But on the other hand, what is written in the table? The total number of permutations of A1, A2, and B. Do you agree? Because if you see them distinct, you have written all possible permutations. But you already know how many permutations are there for 3 distinct objects. Oh, what is that? 3 factorial. So on the one hand, you already know the answer should be 3 factorial. On the other hand, you counted the same number of items is 2 factorial times x. So these two numbers should match because you're counting the same number of items in 2 different ways. This is called double counting, yes? In Combinatorics. So this means that this is what I want you to understand. If you understand this equality, this means that I was able to teach you. Yes? Do you understand this equality should be there? Yes? Okay, but still I am looking for what? I am looking for x. So x becomes what? 3 factorial divided by 2 factorial. And what the answer is 6 divided by 2 is 3. It was a very extreme simple case. Do you agree? Yes? Okay, now let me ask you your opinion about this if I want to check your understanding. So let me make it a little bit different here. So I have this scenario now. I give you 2 A's and I give you 3 B's. Okay, and I ask you the same question. So how do you think I will solve the problem this time? By this strategy, if you understood this. The first thing I will do, I will label them. How many A's you see? I have 2 A's, they are identical, but let me pretend they are not, so give them indices. How many indices I should give to A? A1, A2. And how many indices I should give to B's? B1, B2, B3. Yes? So let us pretend that they are not identical. So I would do that. A1, A2, B1, B2, B3. Okay? So you know that you have to go vertically, according to what I did. You also have to go horizontally. Yes? So vertically, can you tell me how should I go vertically if you understand this algorithm? By the way, this is the strategy you have to follow to be able to do that. You might say that I have a different strategy. Okay, be my guest, do that. But I'm just explaining one possible strategy to do this. So what should I do here? Yes, Dino?
2 factorial times 3 factorial.
Yes, but give me what you are doing, what you are counting. Yes, that's correct.
The amount of rows. So the amount of rows is 2 factorial times.
How do you know that? Because you are supposed to interchange A's among themselves and B's among themselves. In how many ways I can arrange A's among themselves? 2 factorial. In how many ways I can arrange B's among themselves? 3 factorial. Yes? So this means that if I take this item and stick to the rule that I'm only allowed to change A's among themselves and B among themselves, one possibility is A2, A1, but it's still B1, B2, B3. One possibility is to write A1, A2, and B3, B2, B1. I hope that you agree that I am just sticking to the rule. I am changing A's among themselves, B among themselves. And if I ask you what is the depth, I hope that you understand. The ways that I can interchange A's is 2 factorial. The number of ways that I can change B's is 3 factorial. I am doing them together. So the depth here would be what? Oops. I have to bring it back. So here, let me change my color. So the depth, I hope that you agree with me. The depth is what? 2 factorial, the number of repetitions of A, times 3 factorial, the number of repetitions of B. Okay, for example, but you know that all these items should be counted how many times? If I have identical A's and identical B's. From all these scenarios, 2 times 3 is 12. From these 12 items, for my original case, how many of them are acceptable? How many times should I count them?
1 time.
1 time. Yes? So each column contributes 1 to my problem. Yes? So I need to now know the number of columns. But we don't know. Okay, so let me take the number of columns to be x. And I multiply it by the depth of each column, which is what? 2 factorial times 3 factorial. Now I want to ask you, can you tell me what are you expecting this to be? If you answer this one, you understand the problem. So it means that assume that you finalize this strategy item by item. You get a big rectangle of items. How many items you expect from your previous experience, not today's lesson, should be in the rectangle? Yes?
5 factorial.
5 factorial. Is that understandable for everyone? So that's okay, I'm relieved. So this is 5 factorial. But still you are looking for x. Yes? So x becomes 5 factorial divided by 2 factorial, 3 factorial. Is that clear? So this is also something you need to know. It is mentioned in some of the problems in the book. But if you don't need these strategies, it's very hard to answer those questions. Is that clear? So this is permutation by repetition. Okay, but be careful. I am using all of it. Okay, that would be a completely different problem if I say, okay, here I am using 5 items according to definition, but I can say that, okay, use 3 items. Then that's the problem, yes? Because you don't know. You can choose 2 A's, 1 B. You can choose 2 B's, 1 A. You need to consider all those cases as well. Yes? But for the time being, I give you all the 5, and I ask you to use them to find my items. Okay? Is that clear? So can you tell me, for example, now hopefully you understand. Let me test your understanding before going to the next page. If I give you A, I don't know, A, and then B, 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 and C, 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 and then E. If I ask you how many permutations are there, I have 3 A's, 3 B's, 4 C's, 1 E. How many permutations are there? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So how many 11 object permutations you can write from these objects? So just give me answer. You don't need to follow the strategy, by the way. This is the proof of this strategy, but in the exam you can just write the formula. I accept it from you, okay? I hope that you understand what's going on, okay? So can you tell me what's the answer to this directly? From the patterns that you learned in the previous two items, yes?
11 factorial divided by 3 factorial times 3 factorial times 4 factorial times 1.
So 1 factorial, which we don't write. If you write, it doesn't matter. Yes, that's correct. So the total number of items is 11 factorial, but because some of them are repeated, you have to divide by the number of repetition of each item factorial. Yes? So as you said, it's correct. So this is 11 factorial divided by, I don't know, 3 factorial times 3 factorial times 4 factorial times 1 factorial. So these can be combined to 3 factorial to power 2, and I can just drop the 1 factorial because it doesn't matter. Yes?
So if we use this in the exam, it's okay if we just write it. We don't have to explain it or prove it.
Yeah, no. Unless I ask you to prove it, of course.
Okay.
Yes. Yeah. But these are very standard ones, you know, these are not very high level ones. So these are very standard combinatorial problems. I want you to know them. So if you know what you're doing, that's okay. Okay? So now I think I just go to the next page because that is the general theorem and that's the proof. So that's exactly what I said. But if you want to write it in mathematical terms, it becomes a little bit subtle. So consider n objects that n sub 1 of them are of type 1, and then n sub 2 of them are of type 2, and continued n sub k of them are of type k. And n1 plus n2 plus nk is the total number of objects. Then the number of permutations of these n objects is equal to this. So it is n factorial divided by factorial of the repetition of the first items, and then times the factorial of the second one, and etc. and etc. Is that right? So when the time is finished, do you know?
55.
Okay, so let us just solve one example. Okay, so let us do it together. I hope that there is no messing up with Grammarly. Okay, so how many 11 letter different words? Okay, 11 letter different words can one construct with the letters? Yes, with the letters in Mississippi. In how many of them all eyes are adjacent? Yes? So let us try to solve the problem. So you see that this problem I couldn't ask you before. I talked about mailbox, I talked about table. So what is the difference here? In Mississippi, I have a lot of repetition of the same letters. So this is permutation with repetition. Yes? So this is the new lesson. We couldn't solve this before. Yes? Okay, so the way that I do this usually is to, for example, I would say that Mississippi M, I, and then I put two S's, and then I get to another I get two S's, and then another I, and then I have two P, and then I have another I. Yes, am I right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes? So this is the way that I arranged the word Mississippi to understand how many repetitions. This is just my taste. You can do whatever you like to. Yes? Okay, so how many permutations are there for this letter? For this word? You understand this is the new lesson. This is the same problem as before, but some of them is repeated now. So the answer to this is immediately clear. So the answer is what? Just tell me. I have a fraction. How should I fill up the numerator?
11
factorial to the total number of items, but I have to divide by the factorial of the repetitions. Yes, m is repeating once. If you want, you can add 1 factorial. It doesn't hurt. And then how many i's you see? 4 factorial because of that. And then how many s's you see? 4 factorial. And how many p's you see? 2 factorial. So that's the answer. And that's it. You just stop here. I just mark you based on this number. Is that clear? Yes.
Wait, how did you place all the eyes adjacent in this question?
No, it's not finished. Okay. This is the first part of it. Okay. Now that I want to wait for you. Now, the interesting is the second part. Not very interesting. It's not very hard, by the way. In how many ways I can arrange the letters, but there is one constraint. All the eyes should be adjacent. In how many ways? In how many of them, I mean in how many of the first items, all eyes are adjacent. So how can I solve that problem? How should I solve? Now you have a model in your brain, just use it, yes.
You can
put
all the I students
together. Yes. So why do you hesitate? So we are constructing new problems on top of the previous problem. So you want to have eyes in one box. So we solved the problem like this, didn't we? So what I will do, I will take them and put them in a box. Okay. But the point is this. And I will probably put a capital I. I don't know. You can make stories, yes? So I put a big I there, yes? And then I have M, I, 4 S's, and 2 P's. I arrange them, okay? How many objects I have? I have one M and capital I suddenly, which is a box, whatever, and then I have 4 S's and 2 P's. In how many ways I can arrange them?
8 factorial.
So, not finished yet. 8 factorial, because still I have some repetitions left.
Yes.
Even though capital I is not repeating itself, but S and P are repeating themselves. Yes? So I would say the answer is what? The answer is, so let me count. 1, 2, 3, 4, 5, 6, in total 7, this is 1, and then 8. So it becomes what? 8 factorial. But the answer is not just 8 factorial, because even though now I have one capital I which is not repeated, but I have 4 S's and 2 P's. So I have to divide by? I have to divide by?
4 factorial
Times 2 factorial. So that's the answer. Yes? Is that clear? Okay.
So then you don't consider repetition. Well,
No, we consider if you want to, but in how many ways I can arrange I's? All of them are I's.
yeah.
In one way. Or if you want to, you can say, I want to arrange I's, so I multiply by 4 factorial because I have 4 I's, but because I's have been repeated 4 times, so I have to divide by 4 factorial. Yes, that's also working. It's not wrong. But who cares to write that? So I would prefer not to write. Yes? Is that right? Yeah. Okay, so I really like this topic. I remember when I was at your age, I was so excited because most of the time I got the answer wrong. And then I thought that, okay, this is correct. Then when I get something wrong, I actually be encouraged to work on it more. Okay, so I hope that is the case. But you will enjoy this topic if you like it, of course. Okay, so I think I will stop here. So I hope, is it working for you? Is it not disturbing you? I'm sitting here and teaching you here. No? And by the way, I can also publish immediately my notes. So because now it is in PDF file, so I can put it on the Google Classroom. Okay. Thank you very much.